just let me introduce the concept of digital twins, because I think it's important also for all the things that we are going to look at next, because they are pretty much a peculiar system. I like a lot the definition that you see here, so that are the digital representation of the real world system. And this means that, for instance, no, not this one. I I want to say that, yeah, I have a wildfire, and I want to project into the digital world what can happen if a wildfire spreads somewhere. I need a digital twin of the reality to simulate that. Same for the flood impact modeling. And in science, in particular physics, for instance, we also have this need, and it's related to understand how our detector works. So this gigantic camera that are recording everything that happens at microscopic scale, yeah, they are complicated, time consuming and energy consuming to simulate, to understand. Maybe machine can do better and describe our detector with less effort. I say maybe because it's an open field. And same for different kind of activity where you are very sensitive to noise, and you want to simulate the effect of noise on your pictures or on your measurements. So yeah, a lot of heterogeneity already in the use cases that shares a common set of needs. And this common set of needs drive the development of intertwin project. And yeah, an engine that we can share with all the previous use cases, and where we can build one layer over the other with a transparent ecosystem, with a transparent interface. So you can use it for different things, as we saw before. But the most important challenges that we want to tackle today, that drove us to use Dagger for many things, is, okay, we have several frameworks that should be able to use a common platform that can distribute the application for the digital twins. We want to offload the heavy task to a number of remote sites, because heavy payloads should go to supercomputers, for instance. And then we want to maintain kind of an interoperability between all these frameworks. And this is granted for us just using cloud interfaces. And we will see that it's not that simple. Okay, intertwin, you have all the details in the link, so I do not spend more time on this. It's an effort of different communities, that both from the providers perspective, cloud providers, supercomputers, quantum systems, all this kind of stuff, and also community, so who actually builds digital twins.
That's awesome.
Yeah, cool, right?
Yeah, it's amazing. Just the amount of things that are included in that, and you're going to be talking. Both of you have a talk at KubeCon about that project, right?
Yes, we are going to have a similar discussion at KubeCon. There are some extras, of course. I don't want to spoil too much, but it's along this line. So yeah, the project and how we manage this heterogeneity.
Great.
On Friday.
That's awesome. Very cool.
All right, so the challenges, just to recap, we have several distributed heterogeneous resources provider, HPCs, HTCs, so batch system mainly, and cloud, and we want to access them through a common interface. First problem then is how we can access them. And then where Daggers come in is maintain a software that works in a consistent way on all these platforms, on all these backends, is a challenge, and a challenge that we want to take, especially for checking that our images are behaving the same on all our providers. And we ended up already to have a zoology of this image. Some needs a particular format like Obtainer or Enroute from NVIDIA, but also you have environments where you need to load extra libraries to make things work, and so on and so forth. So these kind of challenges are particularly hard to solve in a non-Dagger way, let's say. And on the other side, rightfully, users usually don't care how you do that. They just want to run their things and that work out of the box. On the other hand, the good thing is users also starting, or in science, since a while, converging toward a common set of tools that are cloud native, if you want to name it in that way, for machine learning and data science. So this gives us some knobs to turn. We can play around a situation like that, okay? So everything is converging toward Kubernetes. We can take this and have a plan at least. And the plan is a solution that we are developing in Intertwin that just joined the CNCF sandbox that is called Interlink. So you can imagine like a generic, a universal adapter for Kubernetes to delegate it, to offload your container to a remote site. So you have your Kubernetes cluster, you launch a pod, and the containers will run somewhere else in a batch system, in a supercomputer. I'll go fast on this because it's one of the modules that we are going to use, but it's not the central part of the presentation. So now we have this powerful tool that solves the problem number one of the presentation. We have a Kubernetes interface where we have no CRDs. Everything is transparent. We can just attach a Kubernetes cluster to any remote resources that we can reach. So we define a pod with some configuration, and this will land on one of the supercomputers that is part of the collaboration. It will do the train of some model and will respond with a result in some kind of archive. In this case, is MLflow system. Good. The introduction is finished. We have this kind of tool to be used, and the software that runs on these platforms, on Kubernetes with several frameworks, has to be compatible with all our backends. And yeah, a lot of power, we have a lot of responsibility too. So we need to guarantee our users that everything works just as fine. And so we need reproducible results and a way to orchestrate different workflows for different backends, if you wish. We could do, and we did try to use with the usual CI system, but I think we can conclude that we couldn't do without either being heavily locked in by the internals of the CI system that we used, or in any case, we could not avoid to have a copy-paste nightmare somewhere where you end up with some solution that works, but it's different to maintain if someday change something in the way you build your images, for instance. So we needed a starship, spaceship for our interspace, if you wish, and the solution that we are presenting today is based on Dagger, of course. I think I don't need to introduce the feature that Dagger provides out of the box, but just to refresh, what we were looking for is especially something where we can program our pipeline in a declarative way, where we can manage all the things in the most CI agnostic way possible. And then there are some bonuses that we are glad to have that are caching artifacts. If we need to rebuild new images in different formats, it's good to have. And also the observability to understand what happens. Of course, the LLM, the new cool tool in town, is pretty interesting, and we are looking for that. It will not be presented here, but maybe you will hear from us after the KubeCon.
Maybe Kyle could give a quick intro into the LLM feature in case there's people who have joined who haven't tried it out yet.
Yeah, I mean, if it's not part of this demo, I could show, or maybe Lev's gonna show it too.
We're for anyone who hasn't tried out yet, we did. If people are watching and you're just starting to get to know what Dagger is, we have a containerize your agent channel. So if you have any questions on that, either during these demos or afterwards, that's a great place to go because we can help you out with the use cases like Diego was mentioning.
Yeah.
So, are Kyle going to show something or?
Oh no, keep going for it. Sorry.
Yeah, go
I
ahead.
just want to mention
Okay, okay.
for you watching who don't know about it.
Okay, so yeah, so definitely it seems like we have our reusable workflows. Then for reference, yeah, I leave some details, but Matteo will go through more thoroughly. Okay, so we are at the point where we have our pipelines that, by the way, the other very cool things that we have right now is that we can test the very same machinery just from our laptop and not waiting for the pipeline to run or to waste any kind of resources. So yes, you have your pipelines, an engine that can translate from one scenario to another, pretty cool. And you can already imagine how useful it can be, but Matteo will show you in practice. We have beneficial observability, so we can see even when we try things in local, we can test and we see how it's going and what's happening inside the pipeline. Having this insight is very cool. I will skip this. There is a lot of material. I thought to leave some material too, so we are planning to understand how we can use this to fix basically my typos and when happens and when avoid wasting resources before submitting some task. Or I leave the link. If you pass me any other material, I can add it to the slide later. So, all right. The core of the presentation is that we managed to make these two universes, the Dagger verse, if you wish, and the interspace to talk to each other. And this provides us with some cool features. So we can now execute Kubernetes cluster or Kubernetes workflows on our supercomputers just from inside a sandbox that is provided by Dagger. What does it mean is we're going to see a pipeline that bootstrap and ephemeral Kubernetes equipped with interlink that is going to talk to a supercomputer, a Euro HPC supercomputer in Vega. So for time reason, we are not going to wait and to see everything, but Matteo will show the detail for all the implementation. And we can reuse at this point the very same modules for different backends, just changing the last mile of the implementation. That is really the killing features for us at the moment. Of course, if you can get on board with LLM, we are also very happy. So yeah, I just shut up now. I leave the floor to Matteo and enjoy.
So thanks Diego for the intro, and now let's see more details what we're actually using Interlink and Dagger in this case for. So as I said, Diego and I both work together in this project, but in different parts of it. And what I'm actually working on is developing this library, which is called i2AI, which provides it basically works as a toolkit to help scientists scaling the AI workflows to cloud and specific and more importantly to HPC. Providing features such as distributed machine learning, hyperparameter optimization, supporting frameworks for machine learning logs, so to store and track machine learning logs and models such as MLflow, and connecting, of course, to all the libraries to connect the infrastructure, so to the lower level, and providing also some interface, which could be a CLI or a Jupyter interface. So when I talk about distributed machine learning, I mean running the training of your model, exploiting as much as possible the resources that you can find on HPC. And this can be done using a strategy which is purely data parallel. So distributing, replicating your model on multiple GPUs and have them, let's say, work on different partitions of your dataset, or having a hybrid strategy in which you have both data parallelism but also model parallelism, which is pretty popular nowadays when a model cannot fit in a single GPU, so like very large models. And to do this, we base, let's say, our software on top of popular backends that we call backends, such as PyTorch, Horovod, DeepSpeed, and Ray. Another feature, another key feature is distributed hyperparameter optimization. So in a similar way, we want to exploit HPC resources to run in parallel multiple trainings using different hyperparameters. So starting from a tuning configuration, our trainer will be able to launch, exploiting different multiple nodes. It will be able to launch, different trials and track them over time, stop them, and use using RayTune as a backend. Let's see some examples of scientific digital twins that use this toolkit. So here I'm showing only 2 examples because I have not much time, but we have a use case from the environmental sciences in which they're developing an AI-based hydrological model to forecast the effect of climate change in terms of drought. And the other, on the right, you can see a use case from physics in which we are helping them to train AI-based methods to denoise the signals from the Virgo, captured from the Virgo interferometer to detect gravitational waves. So here you have an example of some, let's say, preliminary results in terms of scalability. So one of the main goals for us is to study the scalability of these models on HPC and to compare how these different frameworks or backends like Torch, Horovod, and DeepSpeed compare for each different model. So we can study the speed up and also the energy consumption, so the energy benchmarking. But as I was saying, we're also interested in optimizing these models in terms of scientific, I'll say, metrics. In terms of, so in order to produce more and more precise digital twins. And so here we have an example of hyperparameter optimization. And with, let's say, the integration in RayTune AI, which is based on RayTune, we were able to improve by almost 75% the validation loss compared to the, let's say, initial guess of the hyperparameter. So this is all to say that we are really interested in developing a toolkit which is able to distribute the workload on HPC resources and like on multiple nodes and multiple GPUs, reducing the overhead for scientists. So the engineer overhead. Okay. So, but how do we ensure that our software is always consistent? This is the main problem. So, as I was saying, what we're developing is an abstraction layer. So the input on the left, you can see we have some sort of scaling configs and tuning configs. So these are provided by the scientists. And then there is our trainer, so the actual abstraction layer, which is based on popular backends for distributed machine learning, such as PyTorch, DeepSpeed, Horovod, and Ray, which will actually talk directly with HPC resources. Okay. So for us, it's very important then to ensure that this yellow box is always consistent and we're not introducing bugs or inefficiencies. So first thing, of course, it's normal. We run some tests, and some of the tests are easy to be run because are kind of simple tests. So for instance, we have an abstraction for loggers. This can be run on your laptop. Same for utility functions and some other tests. That's totally fine. So these tests can run anywhere. But there are some other tests that can actually cannot be run on your laptop. But they intrinsically need to be run on HPC. An example could be verifying that the distributed strategies are assigning the correct ranks to each worker. So here in this picture, we can see how each worker, each process, which is assigned to a specific GPU, is receiving different ranks And these ranks are needed by the workers to know each other and to share information, to share gradients in terms of in the context of distributed machine learning. So first thing we need to make sure that the code is actually distributed in the right way. Another set of tests that we run is to make sure that the collective operations are actually working. And when we perform a gather operation, the result of the gather is actually the concatenation, if you want, of some variables on all the workers. And similarly for the gather or other collective operations. Other tests that we are interested in running on HPC are, for instance, verifying that the checkpoints generated during training are correctly stored and reloaded, and also we perform, let's say, integration tests in terms of concerning training and tuning. So we run end-to-end training and end-to-end training under tuning. So we have a tuner, and each trial can itself be distributed. So we have two layers of distribution. And all of these, I mean, it's pretty obvious that cannot be tested on your laptop, because if you're lucky, you only have one GPU, right? So we need HPC resources to run these tests and to ensure that the software that we are developing is always consistent and we're not introducing bugs, so that the scientists can actually rely on it for their scientific workflows. So
yeah, Matteo, just
yes.
a comment. Just a comment on this. So I think what is also very interesting is that since all these resources on supercomputers are kind of have a cost, of course, you don't want to waste with trivial typos or any kind of problem that you have. So one possibility that we have and we might explore is to have a sandbox environment that also simulate how the supercomputer works. So having all the tools there with similar libraries, so we have kind of a dry run before submitting. And this, of course, can fit into a module. It's not there, but it's one of the possibilities that we keep open for the future. And yeah.
Yeah, I mean, indeed, if you have the resources, or if you're able to simulate them, yeah, of course. So
Yeah, no,
yeah.
you don't have to simulate everything, but at least to be sure that they start, and then you have no trivial issue before submitting the real one.
Yeah, indeed, yeah. So just if you're curious to know how we run the tests, because usually you run PyTest. I mean, the simple tests are run using PyTest, and you just launch PyTest straight into the terminal, right? But in this case, we actually need to add an additional step before. So first, we have a distributed ML launcher, it's called, which will spawn processes on each node, and a number of processes, for instance, equal to the number of GPUs, so that each process is assigned to a specific GPU. And then each process will actually run PyTest, so launch the tests. But each test, before actually running, I mean, since it's meant to run in a distributed, how to say, in a sort of like distributed environment, so it needs to communicate with the other processes. First thing, it will set up the collective communication. It will connect to the collective communication backend, which is actually being the interface to the HPC resources. So this is pretty much the high-level picture of what's really happening under the hood. So let's try to wrap up and put everything together. So how do we actually do all of this in practice on HPC? So currently we have our code and CI workflows hosted on GitHub. But how do we connect GitHub to HPC, or in other words, how do we integrate HPC resources into GitHub? Well, first problem is, as Diego was saying before, if we rely on GitHub workflow and GitHub action and GitHub workflows, it becomes kind of complicated for us to replicate the workflow locally or on any other kind of resource. So Dagger is providing this functionality to abstract out from where you're actually running. And second, very important feature is that it allows to deploy services which are very important because we will see later why. But deploying services into the pipeline, it's a key enabler of our results. So how do we do this? We have a Dagger pipeline which is running on GitHub, and which is deploying an interlink service. I mean, it's deploying a K3S service, on top of which an interlink virtual kubelet is deployed. The containers are built into the GitHub, into the Dagger pipeline, which is running into the GitHub action space. And then at some point, when some of the tests are passing, then the container will be pushed to some Docker registry. And then interlink will make sure that the container is actually pulled on HPC, converted, and the tests are actually part of the tests are actually being executed on HPC. So the tests that need to run on HPC will run on HPC. And once the tests are passing or failing, when tests are passing, the pipeline will continue, and we will so to see in more.
Sorry again. Just to stress one thing, that the other feature that is pretty cool is that to integrate K3S in this case, you had to do nothing at all, right? So you had to import the module that already exists. You look at in the Daggerverse and you import that, and that piece of the puzzle is already there for you. Same kind of with interlink. We are we are going to maintain a module for the interlink installation. So if you wish, the core part comes for free just with the modularity of Dagger, and then everything else is kind of a plugin into that. So this structure is pretty flexible and just what we needed, basically.
Yeah. Let's say, I mean, it was not everything for free, but yeah, luckily now things are good.
Of course.
No, but yeah, I mean, also, but yeah, indeed. The nice thing of the modularity is, indeed, for instance, K3S was indeed something that I just reused as it was. So yeah. So let's look at the pipeline. So what's really happening? So first we build the container. We test it on GitHub. The container is then converted to a Singularity file. It's after the conversion is completed, we deploy an interlink service on top of K3S. We launch the tests on HPC using the Singularity file. So the Singularity, the Docker file, which was converted to a Singularity file. And after that, if the tests are passing, both the Docker container, so both the Docker image actually, and the Singularity image will be pushed to two different registries, just because I mean, you cannot push Singularity images to GitHub Containers registry or to Docker Hub, but that's fine. So in this way, we can actually distribute the containers with our community, and the use cases can also build on these containers. So we have an i20AI Dagger module as well. I put the link below here. And actually, this i20AI Dagger module contains 3 types. So the i20AI type, which takes care of basically the i20AI container lifecycle, the interlink type, which basically is based on K3S. So basically, what Diego was saying before is using K3S under the hood, and then is deploying interlink, starting the server, the service, and so on and so forth. And then we have the third type, which is Singularity, which actually allows to convert a Docker container inside Dagger to a Singularity file, and also push into the publish and so on and so forth. Yeah. Okay.
Yeah.
Forgot to say this.
I don't know. What do you think, Miranda? If we have time, maybe Matteo can go through these modules live.
Yeah, let's check out like one of those modules. But I think this is amazing. I'm honestly just been absorbing how cool it is that like you can build one of these modules, and just continuously reuse, and not only for your use case, but like you've now contributed this type of stuff to the rest of the community too. It's amazing. So build it once, use it for multiple things is always nice.
Yeah,
That's
exactly.
good, yeah.
We can start from where you instantiate K3s, and then interlink just
Yeah,
to
okay.
give you an idea.
Sure, yeah, exactly. So I have everything here prepared in my cheat sheet. Yeah,
Love it.
otherwise I always forget. Yeah. So what's happening now it will take a minute, so let's just have a look at it. So what I'm doing, I'm actually calling the interlink function. So if I go AI is my main module, right? So if I go into interlink here, we will see that actually it returns the interlink type, which I have here. So let's just have a look. So I mean, what's really interesting here is just the values, pretty much. So the values to set up interlink. So it's a secret. In this case, I passed it as a file. So as you can see here. So I'm passing the values to start up interlink. And what this values file contains is, I mean, Diego can give definitely more details than me, but it contains very much the authentication tokens that my local interlink deployment needs to know to connect to the interlink sidecar running on the HPC. So this is as a very important step, because in here I have basically my credentials, let's put it this way, to connect to the HPC, or to the, let's say, to the interlink server living on the HPC. And then so now let's have a look at the interlink. So what's going on in here? Let's maybe move it to the left so I can continue show you. To show you, yeah. Then we have interlink cluster. So this is basically just a service. It's returning a service, and what this service is actually doing. So we actually have a K3s service which has some name, yeah, and that's pretty much it. So we start the service, and then inside the service we actually deploy interlink. So that's how we deploy interlink on top of the K3s. So as you can see in here, we are setting the values. So that file containing all the credentials that I need to connect and to authenticate to the remote HPC, it's there. Yeah, and then that's pretty much it. So we do helm install, and we have an interlink. We sleep a bit, and that's it. So now below here we can see that the interlink service is up. So yeah, I mean, I can probably
So
just
yeah,
have a look.
at this stage you have a Kubernetes cluster running and a node that is not a physical node, but it is the one that will submit jobs to the cluster. So a virtual node.
Let's see if it was.
See
if I
you have
remember.
also the client. Yeah, cool. Okay.
I think so. Yes. Okay. So yeah, of course. Yeah, I need to tell him where to connect. Of course. No, yeah. Interlink. Yeah. I need to tell him. Yeah, it was here actually. Why did I copy the first time? Yeah. So yes, I also have a client. So again, this is something everyone could use, even without having to know anything about it with AI. So you just yeah, what's happening here is that I'm passing the service endpoint to these Dagger functions. So yeah, and basically I'm just calling the the client is just a container and opening a terminal. So if I get the pods, here we have the pod. So that's the interlink virtual kubelet.
And Vega is the name of the supercomputer. It's a Slovenian supercomputer in Europe.
Wow.
And it's also ready. So
That's
so yeah.
Cool. Wow.
That's why it was sleeping before.
Okay.
Wow. That's awesome. And for people watching, like, yeah, sorry, I don't have many words. It's so cool to see this type of stuff. And so it's, for people watching, we're watching also the first time this demo. So we're also absorbing how cool it is.
Maybe if you want to see something more, I have this, but this is kind of quick. So when I was developing this, I always want to make sure that my deployment was actually working. So I created this function, which I just called test of loading, which is running some dummy tests. So one will be a successful pod, The other is a pod which is expected to fail, actually. And the third one, I don't remember. The last one is expected to time out. So I just want to make sure that, how to say, my local interlink deployment is actually, able to, to behave as it should. So let's just get out of the K3S. So okay.
And while you're doing that, question came in. Is this is entirely local, right? So not talking to external compute.
No. I mean, this is on a VM, but it's consider it as it was on my laptop. It's
yeah. The only thing that goes remote is now when we submit a pod that is targeting the virtual node, the Vega node that you see there, then it's connecting, it's sending a request to an endpoint in the supercomputer.
And that's through Interlink, right?
Sorry?
That's through the the Interlink project. Yeah.
Yeah.
Awesome.
Let's see. Let me show you the pod.
The second one, yeah.
Yeah. So now I'm opening the client again, so I can show you that there is a pod, which is actually running in the K3S, and this pod has been assigned to the virtual kubelet, to the Interlink virtual kubelet. So.
That's great. And another question coming in is, what's the local resource consumption like? Would it need a beefy machine?
I mean, to be honest, to run Dagger, maybe a little bit of storage because of the cache, but no, apart from that, no, not much.
No, just to give you an idea, when we do some preliminary scale test of all this stuff, it's kind of supporting order of 1,000 pods running in a matter of 4 CPUs, 4 gigs machine. Nothing special. It's all virtual. I think even the normal kubelet will have extra operation to do with respect to the virtual one. So it's even lighter than a normal kubelet. And yeah.
So in this case, I see that the pod keeps being in pending state, but that's because today the queue on Vega is pretty full.
Yeah, that's the nice thing of the demo.
Yeah, because we're demoing, that's why. No, but this is really cool. Thank you so much for showing this.